Okay, so I switch in English. And so it is my pleasure to introduce Professor Mario Di Bernardo. I had the opportunity to meet in Bari in 2020 when he gave a short course on dynamics and control of complex networks at the Department of Mathematics. Professor Mario Di Bernardo is a professor of automatic control at the University of Naples, a visiting professor of nonlinear systems and control at the University of Bristol in the UK. He currently serves as a deputy vice chancellor for internationalization at the University of Naples and coordinates the research area on modeling and engineering risk and complexity at the Scuola Superiore Meridionale. His research interests include the analysis, synchronization, and control of complex network systems, piecewise smooth dynamical system, nonlinear dynamics, and nonlinear control with application to engineering and computational biology. Today, he will give for us a talk about solving the multi-agent herding control problem, theory and applications. So thank you again for accepting our invite, and I give you the floor, Mario.
Okay, thank you very much, everyone, for being here. Fasma, Andrea, and everyone for inviting me to give this talk. Let me share my screen first. Let me know if you can see my slides in a moment. Can you see them?
Yes, perfectly.
Perfect. So today I'm going to give you a talk on something I've been working on, I started working on quite recently, a couple of years ago, and we are still working on this problem, which is the multi-agent herding control problem. I'll try to give you an idea, a broad overview of what it means, but I would like to start by setting the scene. In other words, by talking about controlling complex systems as a general problem. I'll tell you why I got interested in this idea of herding as a paradigmatic control task for this type of problems. And I'll try to give you a flavor of some of the results we obtained, the intricacies of this problem, the sophisticated scaling laws regulating them, and hopefully also unfolding the interesting mathematical problem behind it. So let me start by talking about the problem of controlling complex systems. And the first thing I would like to start with is to define what a complex system is, because probably the words complexity, complex systems, and so on are among the most abused terms in nowadays science. So let me tell you what I think, or what I'm studying as a complex system. A complex system, and I use the definition of this relatively new paper by Daniel Bassett and co-workers on Science Review, is a collection of objects or agents. So I'm talking of complex multi-agent systems here, typically many of them, which interact with each other in a non-trivial way, and through their communications and interaction, emerging properties, collective behavior emerges that cannot be explained in terms of the simpler individual agent dynamics that, in my setup, can be described by a nonlinear vector field. So for me, agents in a network or complex system such as these are nodes of this network. They are described by a nonlinear vector field, and they communicate with each other via some communication or interaction protocol that can be a linear or nonlinear function of the set capital Xi you see of their neighbors. That means the agents they're connected with. In the literature, you can find plethora of examples of this type of models with different types of functional form for the vector field F, different types of interaction or communication protocol among the agents. Just to give you a flavor of what this UI looks like, here is a very sort of a simple diffusive nonlinear coupling between the agents. What we see here is some common coupling gains between the agents, Aij is an element of the adjacency matrix determining who is connected with whom. And then in this example, agents in this complex system exchange information on the mismatch between some function h of their states x. Now, one of the key issues here is to try to understand how to steer or orchestrate in real time the emerging collective behavior of a large-scale multi-agent system. We have a network of interacting agents, we said many of them, that are communicating with each other. And let's go back for a second to the very gist, to the essential elements of feedback control. Feedback control is about putting together three essential ingredients: the ability to sense the behavior of the system you want to control, the ability to compute some control action to make that system behave in some desired manner, and then you need to have the ability to actuate, turn this logical mathematical decision, the control law, into some physical action on the system of interest. Now, if you think about this and you think about the problem of controlling a complex multi-agent system, solving this problem boils down into deciding a lot of different things. For example, into deciding who do you sense. So what nodes do you measure or sense in order to steer the collective behavior of the ensemble? And also, what type of control you exert and where. So what nodes you are going to control. Also, what do you compute? So this is actually, in a sense, talking about or hinting at distributed control on an unheard scale, on a very large scale. And of course, we want the control to be distributed, decentralized, and this is something I'll come back in a moment. Often, especially in control engineering, we want the control action to be computed online, okay? We call, as you know, open loop control is when you pre-compute your control action and you deploy it on the system of interest. If we now accept this paradigm of controlling a complex system, the key problem is also how to control. Not only what and who you need to control or observe, measure, but also how to control, how to exert this action. And over the years, a lot of different strategies have been proposed. Here I'm just getting to the key concepts, right? If you have a complex multi-agent systems of nodes interacting with each other, you can steer their collective behavior by acting on the nodes, strategies that have taken a lot of names like leader-follower strategies, pinning control strategies. You can act on the edges. In that, it means you can change the dynamics in a feedback manner of the links interconnecting these nodes. Or, especially if you think of natural system, you can think of changing the structure of the network itself, so that in order to achieve stability, convergence, and robustness, the entire network of interactions between these agents is rewired in real time. And here is again one example of an equation where you can see all these three ingredients, because what I'm saying is that I can control the vector field Fi of some of the agents. Typically here, the trick is to achieve or maximizing the effect of the control on the entire ensemble behavior by controlling a relatively smaller fraction of the nodes. You can act on the edges, for example, the strength of their coupling in this example, or you can also think of taking the Laplacian matrix here, describing the graph, and turn it into a temporal state-dependent matrix, something physicists sometimes call adaptive networks. In complex network science, there is a lot of emphasis on temporal networks. So in other words, you can exploit each of these three ingredients of a complex multi-agent system in order to steer the behavior. And for each one of the ingredients I mentioned, you can state mathematical problems like, what is the controllability of such a system? What is observability? What about proving stability and convergence? How do I synthesize the control law? And you know that over the past 10 years or so, a lot of different results have come out, some based on linear algebra and its extensions that still suffer from limitations when you move to fully nonlinear systems and agents dynamics. Also, a lot of underlying assumptions on the structure of the graph, its time invariant nature, the structure of the vector fields. For example, they usually assume to be smooth and so on. And so you need basically to adapt it as time goes by to different types of applications. Now, the final thing I want to say about this problem, that this is a tricky problem because it entails closing the loop across different scales, okay? And I hope this diagram here on the left can help me convey this message. Why is this a multi-scale problem? Because you typically have a set of agents at the microscopic level. Think of a multi-robot system. You have a lot of robots, individual microscopic agents that you can typically control. So you can typically input or control at the distributed level the microscopic agents living here. But what you really want to control is the emergent collective behavior emerging from the interaction among these microscopic agents. And typically the description of these different scales is made via different mathematical tools. For example, at the microscopic scale, one might want to use large set of ordinary differential equations, while at the emergent behavior level, for example, think of density distributions, etc., you might be able, using mean field, to obtain some type of PDE, etc., describing the macroscopic behavior of the system. And there are all sorts of different problems here because the introduction of control inputs on a fraction of the network nodes renders the system highly heterogeneous. And so it depends on what you can do, and classical midfield strategies might fail, etc. So this is an open problem still. After 10 years after Nature, back in 2011, dedicated its cover issue to the problem. How do we attain complexity? I think this is still an open problem, and I believe that one of the issues is to sort of bridge the gap between these different scales, exploiting, for example, the mesoscale, that is a scale that physicists refer to quite a lot, but that in control is not really used, controlling at the level, for example, of clusters of nodes or community of nodes or something like that. Now, as a paradigmatic example of collective behavior emerging from the interaction between these nodes at the macroscopic level, I became very interested a couple of years ago on herding behavior. And herding is a very sort of common emerging property and behavior in complex multi-agent systems. It has been studied in a lot of different areas. For example, people talk about herding in financial markets, where buyers start buying or selling the same stock suddenly all together because of environmental perturbations, imitation of neighbors' dynamics, etc. The same true in animal or crowd dynamics, where you can see the emergent formation of herd, etc. And models over the years have been proposed to explain the emergence of this phenomenon. But there are several circumstances where this phenomenon is induced by other agents. So there are a lot of examples in applications where it can be advantageous for a group of agents. And so we are moving a little bit away from the paradigm I just illustrated as the paradigm of controlling complex systems. And this group of agents is entitled or is tasked with the objective, with the goal of controlling the collective behavior of another group of agents. Typical example, this is a funny movie I found on the internet, the idea of shepherding, dogs and other agents shepherding a flock of sheep so that they take some desired forms or shapes or move in a desired manner. Or think of a behavior often observed in prey-predators interactions, where predators will try to actually encircle and entrap and herd the prey into some desired direction. But the same is true also if you think of interactions in search and rescue operation following a natural disaster or fire, where you might want autonomous artificial agents to track and herd a group of agents, take them to a safe region, etc. Or even if you think of the continuum limits, and I will come back to this, when you have a very large scale number of agents that need to be controlled, you can think of operations where you try to contain pollutants in the ocean, microparticles, microplastic, etc., etc. So this is what is, some people talk about shepherding problem, herding problem, containment problem, encirclement problem. The literature abound with a lot of definition for this problem. Why do I find this problem interesting? Because if you go back for a second to what I said at the beginning of this talk, a complex multi-agent system can be controlled by controlling a fraction of the nodes, or maybe changing the dynamics or the functional form of the coupling between the nodes, or the structure of the network, to a problem such as this, where you have two complex systems, the controllers and the targets, that need to observe and control each other. In other words, the red controllers here are tasked with the problem of measuring or sensing the collective behavior of the target agents and steering appropriately their collective behavior in a desired manner. This is precisely what the herding control problem is all about. And in order to, for the sake of clarity, I am actually embedding this problem. I'm giving you this problem in the framework of a planar example, okay? In the planar herding control problem, a group of agents that here you see depicted in yellow, that I will call the herders, sometimes they're called the drivers, especially in the mathematical community. Well, these yellow agents need to corral and group the green target agents towards some goal region of the plane. This is what they are tasked to do. Of course, this is one of the simplest scenario here. I'll show you some others in a moment. So our problem is that of solving what some people call an indirect control problem, right? Because we are controlling or driving the dynamics of the herders, the yellow agents here, in order to steer the dynamics of the green agents, the targets. So we are indirectly controlling the target behavior via steering the dynamics of this group of herders, okay? Mathematically, what I mean is a kind of indirect control problem where if we call yj the position in the plane of the jth herder, these for me are autonomous artificial agents, and I've got nh of them, and we call xi the position in the plane of the targets, the problem is to design the dynamics f of the herder agents so that given the vector field G describing the dynamics of the target agents, we can achieve some desired goal. For example, in the simplest case, we want all the target agents to enter in finite time some goal G of the plane, okay? Now, in the literature, you find many variations of this problem. Just to give you an idea, people talk about containment if you want to push them towards a convex hull surrounding their center of mass, herding when you want to take them to some position, navigation, encirclement. And of course, this goes back to the old days of pursuit evasion games, where, you know, the multi-agent pursuit evasion is there are still quite a lot of open problems in that arena. So we have different types of tasks, but it's very clear that what we need to do, given the dynamics of the targets, is to decide how to control the dynamics of the herder in order to achieve some desired task. And This is a type of control problem you see in many practical applications where you cannot directly control a set of agents or individual, but you need to use a second group of agents to do the control for you. So, and please do interrupt me at any time if you have any question or comment. So let's move one step further. The first problem is to decide the target's behavior. And I'll use the next 5 minutes or so to give you a little overview of the existing literature, because really the problem has been studied over and over again in mathematics, in several areas of engineering, in physics, and so on. So I just want to give you snapshots in the existing literature to show you what our approach has been. So the first issue is the target's behavior. This is something that you cannot decide. There can be animal groups, there can be humans moving, it could be other agents. So the motion of the target is typically given to you and is affected through some interacting potential fields with the position of the herder. So typically, if this diamond is the herder and the target is this purple circle here, the target will feel the effect of the herder, so will feel a repulsive or attracting force exerted from the herder onto the target only if they're close enough. This is typically a typical assumption made in the literature, right? So we have some dynamics for the targets that determines how they react to the herder and also how they interact with each other. And this is a crucial point. Most of the results in the existing literature assume that targets tend to flock together. Think of sheep, for example, in the example I gave, but also in other areas of applications, the assumption is made that targets, when alone, away from the herder, tend to flock together. This makes the control somehow easier. Okay, it's not an easy problem, but still, flocking assumptions mean that you can look at the barycenter, the center of mass of the flock, and then push the flock by acting in that direction, right? This is an unrealistic assumption in some circumstances. If you think of the application of this to search and rescue operation, or to the control of crowds, I mean, to make sure the crowds go in a certain direction, etc., in the presence of natural dangers, think of a fire, the agents, the target, will start scattering away. Okay, so what the artificial agent need to do is to try to induce flocking, induce this collective behavior in a decided manner. And so the issue here is how to decide the dynamics of the herders, right? How do we move? What kind of local distributed feedback control laws can we design for the herders, here represented by these blue diamonds, to move in the plane in order to push the herders, the targets, the purple circles, into a goal region of interest, right? And you can see that this can be done in many ways, but it requires some degree of cooperation between the herders that need to implement some collective decision-making in order to decide, for example, and I'll come back to this in a while, who is going after whom, right? Think of these situations. We have a certain numbers of targets in purple. We have 4 herders. The first thing they need to do is to cooperate in order to decide what agent they go and target, right? And what is the sequence of agents that they will actually go and influence in what way. So an intuitive solution proposed in the literature is to rely on some type of formation control, or, and this is, for example, something that is fascinating optimal control problem, into pre-computed optimal control solutions. But for real applications deployment, you really want, and robustness, I'll come back to this, you really want the solutions to be such that they can be deployed online. So you really want to do real-time feedback control of the herders dynamics in order to solve the problem. Of course, one solution is to set up a set of virtual attractive or repulsive forces between herders and targets in order to solve this problem. And let me give you a very quick overview of what has been done in the literature so that I can then introduce what we've been doing ourselves. First, let's start with the simplest case, one herder and one target. This is a typical example that is basically studied in the robotics literature. Even in very recent papers, you have the case of one herder who needs to drive the behavior of a group of flocking targets under the assumption that the targets are flocking. Here you see a picture of a real experiment with a robot herding a group of geese, right, of birds, under the assumption, as I said, that the targets are flocking together. You can see that I don't want to get the details of these equations, but just to point out that what you see here is the central mass of this group of agents that can then drive the dynamics of the herder, because the herder aims at driving the center of mass and doesn't worry too much about the individual dynamics of the target agents. Because of their tendency to flock together, you then control the flock, okay? Something like containment control. You get something already, some internal dynamics to the target agents that make them stick together, and then you push them in that direction. Of course, the interesting problem for me is the multi-agent herding problem. What if you have more than one agent and you need to control their behavior? And interestingly, here I give you some example of the earlier literature. In the early literature on the multi-agent herding control problem, typically path planning or some type of dynamic programming solutions were pre-computed online in order to determine how the herders that you see here through this little cartoon had to position themselves in a formation, or by tracking, going to the closest one to them but farthest from the containment region. But these are all pre-computed trajectories, right? So this can be quite computationally expensive, is not easily scalable, and most of all, relies often on the assumption that you have this flocking dynamics. More interestingly, in the mathematics literature, you find a lot of results led, most notably, I mean, Enrique Zuazua studied this in greater detail, but there are many other results. I'm just mentioning one as an example, where he tries to solve this problem again by pre-computing the trajectories of the herders. Here you see from this paper of theirs, the case of one herder, 5 targets. These are the initial conditions of the targets. Here you see the trajectory of the herder that does encirclement and then pushes the targets. But the targets are flocking together. And therefore one herder can move 5 targets in the desired direction. Again, I will not go into the mathematical details here, but what they show is that they can solve this optimal control problem, assuming just that the herders are avoiding collisions, pre-computing offline these solutions and deploying them. Then they do something which is quite intriguing. They observe the maneuvers like this encirclement one that you see here, that the herder is doing, is circling around and then is pushing them. And on the basis of these observations, they try to derive some feedback control laws. But they notice, and this is what they say in that paper, that if the ensemble of evaders, they call targets evaders, are not flocking together initially, then this strategy can hardly work, okay? So the full feedback strategy, when you want to solve this problem online, still has problems in the presence of these, when you relax assumptions on flocking, etc., etc. So what people have done in parallel to this, and this intrigued me quite a lot, was to look at bio-inspired solutions. For example, in this set of papers by Magnus Egerstedt and others, they studied models to replicate the biological behavior observed in groups of dolphins preying, foraging for food. So they notice that sometimes they form platoons like these that encapsulate the prey. Sometimes they start encircling them, etc., etc. But the most intriguing thing to me, the one that made me start working on this problem, was this set of experiments that were, I saw a paper in PNAS in 2019 on this, where a group of experimental psychologists interested in decision making for humans, starting looking at modeling this type of scenario. You have two people, two human players. The targets that you see here are these white dots. They move the herder, so the humans are the herders. Either like this in the lab or through virtual reality, they monitored how the humans, two humans, which are not able to talk to each other, and tasked with the problem of solving the herding problem, solve the problem. And they noticed the emergence of two very interesting solutions that I want to see. This is from their paper. At the beginning of the trial, so this is human one, this is human two, they move these little squares, right? And these are the diffusing herders. So the herders here, this is a very nice thing, do not flock. They are randomly diffusing away particles. Look at what humans do. I hope you can see the video. They start at the beginning of the experimental trial by pushing the target agents that are farthest away from them. You can see it's what they call a search and rescue operation. They start moving these targets, pushing them, try to control their behavior in this way. But some groups of people, some pairs of people, discover a very efficient solution. They discover that once they have collected these agents together, they can start oscillating around them at some right frequency that somehow it's a frequency that emerges out of their interaction because they cannot communicate, right? That creates a containment field targeting and herding the targets. You see that? So, and interestingly and amazingly, because these are people in experimental psychology, they came up with a model that you can find in this paper in the Proceedings of the National Academy of Sciences of 2019, which is the beginning of my involvement with this problem. So what they said, okay, let's set the model in planar coordinates. Yj is the position of the herders, so modulus and phase, rho I phi, the phase of the targets. Then let's write these equations. I will just show you what I mean by that. So they have a radial and a phase dynamics for the herders that it's typically, you can see the terms of a mass spring damper here, nothing special. Don't worry about psi. This is a heavy side function that assume it's always one. And depends on the rho tilde and phi tilde, which are the radial and phase position in the plane of the target that this herder is going to track, right? But then what they wanted to do, they wanted to encode in the model this transition from search and rescue to oscillations. And so what did they do? Which is something quite peculiar. They introduce in the model two nonlinear terms. You see them here, typical of a van der Pol-Rayleigh oscillator, right? So some nonlinear terms to induce the emergence of limit cycles under some parameter perturbations. And then they realize that this parameter b theta, the damping, is a bifurcation parameter. And if this parameter is above certain threshold, you will get Hopf bifurcation. And so you will get the onset of oscillations. If it's below a threshold, you won't get instead the oscillations. And so they did something crazy. I don't think anyone would have ever thought about doing that, of writing an adaptive law for this parameter that changes its value as a function of the distance of the target from the containment region, So that at some point, when the parameter goes a threshold, you get a Hopf bifurcation. Of course, this requires time scale separation, but there is also some coupling with the other herder. Look, their model works. This is their model simulation. And they were also able to make the model play against people, against humans, inducing precisely this transition to the Hopf bifurcation. And here the story goes, I had a problem with this type of model, right? Because you are encoding the behavior observed in the humans, and all of these solutions, bio-inspired or not, suffer from a lot of limitations. So what is the problem with this type of model? Is the model written ad hoc to explain phenomena you observe in these experiments, but you are inducing oscillations by encoding nonlinear terms and causing the onset of a Hopf bifurcation, right? Other solutions assume that the targets are flocking, or that the herders have infinite sensing ability, or even that they don't worry about the scalability. What happens if the number of targets increases? And as I said, many results aiming at proving convergence really achieve open loop, not closed loop feedback control of the targets. So this was the starting point of our work. We tried to look at this problem, okay? Finding solutions to overcome systematically these limitations. And more crucially, if you go back to the fact that this is a complex system, my motivating crucial research question was, do we need to encode in the model the transition to Hopf bifurcation in each of the herders, right? Or can we exploit the fact that simpler control rules at the agent microscopic behavior level could make a macroscopic behavior emerge that includes oscillations, right? It's the whole point of controlling a complex system. You don't have to encode in the model what you want to see, but by simpler rules, right? We know that complex collective behavior can emerge, and I wanted to find out whether this complex collective behavior could be used to solve the herding problem. So here is what we did. First of all, removed the assumption of targets flocking or staying put in the absence of herders. So for us, the targets are now randomly diffusing, stochastically diffusing particles in the plane. So they move away and they feel the influence of a herder with some nonlinear function. Imagine a bell function, so that if the herder is close enough, that interaction function becomes strong enough. What we want to do is to design the control of the herders in order to solve the problem with a number of targets that can vary. This is the issue. So I start by showing you how we remove this assumption of flocking. And what we did was starting from the model I just showed you, right? Simplifying it, essentially removing any nonlinear, removing the need for coupling with the other herders, removing the need for an adaptation that induced the Hopf bifurcations. So now these are just herders in the plane that try to target the agents defined by these elements, rho tilde and phi tilde. These are the positions in the plane of the agents that you want to target, okay? So what you see here is the same model. Rho tilde and phi tilde are the position, define the position in the plane of the target that agent J wants to control, okay? Of course, this is not enough, because if you do this, then each of the herders, if you have more than one, will follow its rule independently from what the others are doing. So we complemented this mathematical model with a target selection rule. In other words, we defined a rule with which each of the herders, the yellow agent, can decide who is going to target next. Okay, so this is another, I am a herder, I have a way of reaching a target, but where do I go, right? In other words, in my model, how do I select those terms that determines in what direction I move, what herder, what target among the many that there are, I'm going to follow and push. This is done in the existing literature via, again, the solution of some optimization offline problem. We wanted to have something simpler, some very simple, the simplest type of cooperation rule for the herders. Of course, you can have some very simple strategies to allow the herders to select what targets to do. For example, you can do a global search. Each of these herders goes for the target closest to itself that is farthest from the goal region. But this requires global information. Everybody needs to know everything. Or you can do a static partitioning of the plane where herder 1 only looks at the blue region, herder 3 only at the green sector, herder 2 only at the pink sector, right? But this is not efficient because targets here are not flocking. They're moving randomly. They tend to diffuse. They move from one sector to the other. So we defined, I will just show you the concept rather than the equations. We defined a way in which targets can, herders, the yellow axis, can self-determine the sector in which they're looking for targets. In a first strategy that we call leader-follower strategy, what they do, they assign or elect a leader, the leader decides the sector, and then the sectors of width that is fixed is determined by the movement of the leader. So imagine the leader as this sector here moves around, everything rotates according to the position of the leader. The other two herders, 2 and Y3, will follow. The other possibility is instead a peer-to-peer target strategy selection where there is no leader. Each one of them looks at what the neighbors are doing and determines the width of the sector in which targets are looked for. Okay. Now, as a result, our strategy combines local control of each of the herders with a selection strategy that makes them correlate somehow. We tested this numerically and also in experiments using an online platform called Robotarium. And we saw, I don't want to waste too much time here, that as you can see, the two herders, this one and this one, are moving around. They are, say, in this simple case, there are only 2 of them to simplify. They are assigning themselves their regions of competence, negotiating it with each other, and then they go for the targets that you see here, surrounded by the green region, in order to push them in the desired region. Of course, the problem here is that we really want to scale this up to a large number of agents. And so by defining some appropriate metrics, we were able to compare these various strategies. Don't worry about the details here. It's basically metrics determining how fast they are in solving the task, what distance they cover, etc., etc. But I want to show your attention on these. What we found is that when you couple local control rules with these dynamic selection strategies for the targets, oscillations emerge without any need to encode the Hopf bifurcation into the solution itself. And why was this quite intriguing for us? Because then when we looked at scalability, here you see what happens when I increase the number of targets from 5 to 60 and write even larger numbers. These simple yet effective local control rules, coupled with this cooperation that is dynamically selecting who is going after whom is quite efficient in solving the problem. And is even, of course, much more efficient when you look at the distance traveled and so on than static or global strategies, okay? But of course, this is only part of the problem because the selection rules I showed you are very simple. Humans, and I will show you them in a moment, I don't want to run out of time, so let me go straight to the point. Humans can do many more things. Look at these two humans solving the problems. They do a target selection. They go after targets with a very intriguing strategy. And so I don't have time to go into details about this, but we used artificial intelligence and learning to try to understand what features, what are the mathematical variables of the model that we can think as those key features that humans, when solving this type of problems, are solving. And so just to show you the idea was to train artificial neural networks to solve, to identify the targets, and then couple them with the mathematical model. So this is a hybrid model. There is a neural network and there is a set of ordinary differential equations talking to each other that, as you can see in this graph, when coupled together, are much more effective. This, you see that the solution to the problem is much faster and with much less variance among trials than what we observe when we use a pure mathematical-based target selection strategy, okay? So I hope this shows you, convinces you that the herding problem can be solved by a mixture of these two types of strategies: local strategies controlling the herders and the target selection strategies making them cooperating. But, and this is the last part of the story, the issue here is that we are assuming here that targets have infinite sensing, right? They can see everything. And this is a very strong assumption. And probably this is why you see that when increasing the number of targets, things do not change that much. The things are very scalable. So the thing we are working on now is to try to understand what happens if the herders have limited, okay? And this is typical in more realistic settings. Can this effect, so what is the effect of removing infinite sensing hypothesis? And in particular, what is the effect on herding? Can it still be successful? Is there then a difference so that there is a threshold number of herders that is needed to control a given number of targets? And in order to do that, we are working now on a slightly different model. I'm asking Andrea and Fasma if I have a couple of minutes. Do I have some minutes more?
Yes, Mario, you have some minutes more, of course.
Okay, so 2-3 minutes to tell you the rest of the story.
Of course.
So the model is, again, no flocking. These are the targets by themselves. They will diffuse away and eventually fill the plane. The targets are described by this set of ordinary differential equations. This is their own dynamics. And this term here determines how they interact with the herders. We choose here an interaction with the herders that is a typical potential centered on themselves. Only when the herders are within a distance lambda from the targets, they feel their presence, okay? We need to design the target, the herders dynamics, FH and IH. And this time around, in the presence of limited herding, we looked at the data available in the literature, and what you saw earlier on showed you that herding is achieved by the combination of two types of maneuver. The herders encircle the targets, and then they push them towards the containment region. And in order to do this, they exert two types of behavior. They search and collect the targets, and then they create those oscillatory fields. So we tried to encode this behavior in the simplest possible model we could come up with. This is work I'm doing with my student, Andrea Lama, who is a physicist. So we are exploring this issue at the interface between physics, maths, and engineering. And we came up with a very simple model for the target, for the herders. First, we give some assumptions on the initial configurations and conditions of targets and herders to simplify things. And then we assume a very simple dynamics. Again, I'm giving you the polar coordinates representation of the model, very simple linear dynamics with the fact that this basically is an oscillator wherein there is no damping. When there is damping, they will tend to an equilibrium whose radial position is determined by these R safe. And by playing with the parameters, in the absence of targets, the herders will go and then circle the region determined by this radius R safe here. Of course, let's put the herders in, let's put the targets in. So what happens that this model is modified by target selection rule. Don't worry about the details. This just picks the most dangerous target in the sensing area of the herder, okay? That is, in the sensing area of the herder, the target which is farthest away from the containment region. Once you isolate the position in the plane, R hat and psi hat of this target, the model, the closed loop model of the herder dynamics is this one, where you can see that now that simple linear dynamics is driven by the position of the targets that you're pushing, right? And this is, of course, for all the herders and for all the targets. Now, you see, the problem is more intriguing mathematically because you have a parameter phi determining the sensing area of the herders. You have a parameter lambda determining the repulsion felt by the targets when the target fits the repulsion. And you also have the density of the targets in the plane. And indeed, you can immediately see that, let me show you a couple of movies. Here, under certain parameter choices, the herders move around, you see in red their sensing area, and are able to actually solve the problem, contain the problem, given the repulsion area felt by the targets and the sensing region of the herders. These 5 herders are able to contain 50 targets. But if you change those parameters, look at the video on the left, of course, the task is not successful anymore. So with Andrea, we are trying to understand how and what values of these parameters, what is the scaling laws that underlie this problem, right? That makes it successful sometime and not successful in other circumstances. And I will show you some results on what we are now called the herdability problem, that we believe is a problem that goes beyond the specific choice of the dynamics. It's like a controllability problem. Indeed, Enrique Zoazua, in some of his recent papers, talk about the controllability problem. Here we are doing it with a slightly different flavor. That's why we call it the herdability problem, right? Let me show you very preliminary results. In the presence of infinite herding, we found a scaling between the number of herders required to herd a given number of targets. They scale as the square root. So given n, here I'm plotting the square root of the number of targets. As you can expect, when there is infinite sensing, there is a linear scaling law, right? The more herders you want to, the more targets you want to contain, the more herders you need, right? Scaling as the square root. This is something we intuitively understand, but we cannot prove yet, okay? Now, let's move to the finite sensing. Look how beautiful this is. When there is finite sensing, this picture changes dramatically. And above a certain number of agents, when the density of the target agents is large enough, you regain this linear relationship, right? It's actually quadratic because it's a square root. But in certain regions, blue is success and yellow is success and blue is failure. Look here. If I have 6 herders, right, and I take this section, what this is showing you that there is an optimal, or if you want, there is a region, there is a optimal density of the targets where the task is successful. Now, I was expecting if there were too many targets, then you need enough herders, so you lose the task, right? You're not successful. What we were not expecting, that when there are few targets, the herders cannot solve the task. And so at the moment we are trying to mathematize the problem to try to estimate or get at least an analytical estimate of this scaling law, of this containment region that I showed you here. So apologizing for being a few minutes late, this takes me to my conclusions. I hope I convinced you that the herding control problem is a very nice paradigmatic control problem in controlling the collective behavior of complex systems. I know, Fasma, that this is a working on epidemiology. I think there is herding goes quite well beyond movement in a plane. So yeah. I guess there is something that connects these also with the epidemiological problem. The solutions is to use a set of simple local rules in order to exploit the fact that complex systems show emerging properties. And right now we are working on this thing of the infinite sensing. But problems abound, right? There are many, many open problems. Optimality, herdability. When do you switch from search and rescue to oscillations? What about the continuum approximation? When the number of tasks scales n to infinity, then you have all sorts of hybrid problems, ODEs, PDEs, there are all sorts of technicalities to be solved. And also, what if you have 3D scenarios? Here you see a movie of agents that need to target. So you have the further problem of exploration, navigation, multi-agent pursuit evaders games, etc., etc. With these, if Fasma, you want, I can give you a copy of the slides. So I've got some references. Let me end by thanking my co-workers. This is funded by funding we have at the Scuola Superiore Meridionale, at the University of Bristol, and Macquarie University in Australia. So I would like first and foremost to thank my students, Fabrizia and Andrea, that worked on these, my co-workers, Davide in Naples and Mike Richardson in Macquarie, for their help and support. And thank all of you for the attention. Thank you so much.
Thank you, Mario. Very nice talk, very interesting talk, and very nice topic. And so I ask to say online if there are questions, remarks, curiosity. And so just I start with a curiosity. I mean, all this
Yes.
approach is based on repulsion assumption. Yes. Is this because the attractive? I was thinking about pifferaio magico. Is this a more simpler approach when you have an herder who is attracting, so that it can easier move the group in the direction that is the target? Or
yes,
it's a simple problem, a mathematical problem, so it is not interesting at all.
No, Fatma, I think it's a very right question. Here, the repelling is due to the fact that we are thinking of applications where you have these moving away, diffusing targets, and we are thinking of artificial agents. So we come from the idea that this could be deployed, for example, in robotics, multi-robot systems, where you have this carrying effect. And so there is this repulsion. In some work I'm doing, I didn't have time to show it to you on the continuum limits. We're also playing with interaction kernels that actually involve attraction rather than repulsion. And you see very different things. Actually, one of the intriguing things is that if some of the herders are repelling and some others are attracting, you can even do better than what you can do with only repelling herders. But at the moment, we are not studying that problem. But indeed, it's a very interesting open question, I think.
Thank you so much. So please, other questions?
I have a
Please, Fabio.
question.
Yes, please.
I'm Fabio Bagagiolo from the University of Trento. Thank you for the seminar. And if I understand well, sorry? If I understand well, the targets are not decision-making agents. So they have a fixed evolution dynamics, depending on the position of the other agents, but they cannot decide.
Yes, Fabio, you're right. At the moment, we are not looking at multi-agent pursuit evasion games. So the evaders, in a sense, they only react to the herders, but contrary to what sometimes is done in the literature, for example, it's assumed that the targets only react to the presence of the herders. So when the herders come close, they move away. Here they have some own dynamics, and the own dynamics is a diffusive stochastic dynamics that scatters them away from the center of the plane, right? So at the moment, we add these as an additional complication to the problem. They do not flock. That's the most important thing, that we are relaxing the assumption of flocking. Because they are stochastically scattering, diffusing away agents, they do not flock, and so all the results that are based on the central mass, etc., here would fail. In fact, there are some others in the literature that I didn't mention, where you can see that in multi-agent herding problems, they need to assume that the number of herders is equal to the number of targets. While here, my only assumption is that the velocity of the targets is slower than the velocity of the herders. There is this assumption that I made, but the rest is not. They're not flocking, they're just scattering away. Of course, a very interesting problem would be to study the case if they do evading maneuvers. But then this goes back to multi-agent pursuit evasion games, and there is a literature on those, and at the moment we're not looking at that type of problem.
Okay, thank you.
Thank you to you. It's a very important point. Thanks.
Further remarks? Further questions?
May I ask a question?
Of course, Mattia.
So thank you for the seminar. I would like to ask you what is the cost of this control? Because if you want to control a high number of agents, at that point is very important to have a cheap cost. And usually in multi-agent systems, I mean, the computational cost is very high. It's at n squared, where n is the number of agents.
Yeah.
And then, I mean, the cost becomes, I mean, unfeasible very quickly.
Yeah. Yeah.
So,
Yes, thanks, Mattia. This is another very crucial point. As I said, we are working on the problem. So we haven't done a computation yet, looked yet at the control effort, which is something we want to do. What we looked at was keeping the computational cost at the individual herder level simple by avoiding solving optician problems online, or so that's why we use a set of very simple dynamic selection rules. We characterize the amount of information needed and these other things in our paper, but I haven't yet looked at computational cost or control effort as such in a rigorous way. It's something absolutely that needs to be done.
Okay, thank you.
Thank you.
Further questions? So if I have just another curiosity, I'm wondering if you have any some reason, some intuitive reason, because of the fact that the heritability cannot be assured when in the case when finite sensing is used. I mean.
Yes, we are actually looking at some graph theoretic based ideas at the moment to explain that. But basically, it's this issue of this region here. What happens in this region is that if you think about it, it's a matter of density of the number of agents as well. When you have finite capability, sensing capability, a finite sensing radius, and each of the target as a finite region surrounding them where they feel the repulsion, you need to have enough of them in order to actually contain them, right? Because then what happens is that you can think of, the way I see this at the moment is you can think of the convex hull that contains the agents, think of the border agents, and what happens is that you need to have enough agents in order for the border ones that you are controlling to contain the rest.
Okay.
That's at the moment my
I see.
intuition about the problem.
Thank you. Other questions? So if not, I thank you again, Mario, and I give the floor to Andrea for the final